Firstly, I just want to thank Dr. Damer and the rest of the conveners of the session for inviting me to give this talk, which is going to be, as Bruce mentioned, on the fates of nucleobases in warm little ponds delivered by meteorites and interplanetary dust particles, so the so-called exogenous delivery hypothesis. Can I use to change this thing?
Yep, the green button.
Okay. Okay, so let's motivate this. Why ponds? Why do we want to deliver to ponds? Why not deliver to the desert? Why not deliver to the ocean? Well, there's really two main reasons. The first being that these are actual locations where you might be able to do concentrated prebiotic chemistry. The chemists in the room could probably attest that you can't really do prebiotic chemistry with parts per trillion level concentrations. You need something more substantial. And these are some locations where you could possibly get them just due to the lower volume within ponds. And the second and most important is that these are locations that have wet and dry cycles, which is key for polymerizing RNA. And Dr. Paul Bracher told us this morning about the condensation reaction and how in order to make photodiester bonds, you need to remove water. So unless you have these alternating wet and dry environments, then it's hard for you to make those bonds. Okay, so the driving question of my research for a long time has been, how did nucleobases arise in ponds on the prebiotic Earth? Why are we interested in this question? Well, in the RNA world hypothesis, we're really trying to get to a self-replicating RNA molecule. So maybe one of the most obvious questions you could ask is, well, then where did the building blocks of RNA come from? Nucleobases are these characteristic molecules in the building blocks and nucleotides, and there they are attached to the ribose phosphate backbone. I skipped over some details there. It is not trivial to get to a nucleotide in a pond from just a nucleobase, ribose, and phosphorus source. But I want to point your attention to some recent experiments that many of you probably know about, which may have had some success in this. This is Nam et al. These are both PNAS articles where they have reacted nucleobases, ribose, and phosphoric acid in microdroplets in order to produce nucleosides. And then there has been a wealth of experiments in the past which have had some success in phosphorylating those nucleosides. And I point you to a review by Gull et al. 2014 for those results. So back to the main question. How do nucleobases arise in warm little ponds? What are the sources? You can really break these down into two types of sources. You have your delivery from space, so your exogenous delivery hypothesis, and then you can also have the production on the planet itself. For exogenous delivery, your two options are meteorites and interplanetary dust particles. Meteorites have been analyzed to contain nucleobases, and IDPs are thought to also perhaps contain the same molecules. And then for endogenous production, you have photochemistry in the atmosphere. UV photons can be absorbed by methane and nitrogen molecules to break them apart, and those radicals that form from that react to form hydrogen cyanide, which once it dissolves into rainwater and falls into ponds, could possibly, through aqueous chemistry, produce nucleobases. Lightning chemistry can do the exact same thing. The only difference is you're changing the energy source, which is creating those radicals which react to form hydrogen cyanide. So this is what I'm working on right now. This is a work in progress. We've built a chemical network, a hydrogen cyanide chemical network from the ground up using quantum computational chemistry methods. And we found many reactions which have not been seen in literature before. So I'm hoping to show you some results from that sometime in the very near future. But for today, let's focus just on the meteorites and the interplanetary dust particles. So, why these sources? Why think about nucleobases being delivered by these sources? Well, as I mentioned before, many works have analyzed them for nucleobases, and we know they can reach the surface intact. The most obvious reason is because in Antarctica, people literally go and search for them and pick them up. So we know that they landed there intact, but other theoretical models have found that if you're a meteoroid entering the atmosphere and you're about 40 to 80 meters in diameter, you're kind of the key size for you to break up into fragments and actually reach terminal velocity and kind of fall down into ponds just intact. A major study, benchmark study by Carl Sagan and Christopher Chiba found that IDPs are actually a major source of organics, so it's important to explore these as possible sources as well. So what did we do? Well, we built a numerical sources and sinks model of a warm little pond in order to ask the question, what concentrations of nucleobases can you actually reach in ponds? Is it comparable to what chemistry experiments can actually do? So here we have a schematic on the right and on the left, if you prefer looking at things in tabular form. I'll just walk you through these sources and sinks for pond water. We have precipitation, and the sinks are evaporation and seepage. For nucleobases, we're comparing meteorites and IDPs as sources, and for sinks, we have hydrolysis, seepage, and photodissociation. We get the rates for these sources and sinks mostly from experiments. However, in the case of precipitation, we use the historical precipitation record, and for the mass delivery by IDPs and meteorites, we use the lunar cratering record. So let's go through the results. On the left here, we have the pond water level. And what we notice is there's actually a lot of degeneracies in our model. For instance, if we model as an analog for the early Earth, Colombia today at 65 degrees, it actually overlaps with Thailand at 20 degrees. So instead of trying to cover all different temperatures for a hypothetical early Earth and precipitation amounts, we just modeled 3 different environments which have many degeneracies. We call them a wet, an intermediate, and a dry environment. And notice in the intermediate and dry environments, you actually get natural annual wet and dry cycles. So that pops out just due to the data. We didn't impose that. That's just due to the changing precipitation on the Earth everywhere on the Earth today. On the right, you can see the adenine concentration from just IDPs within warm little ponds. And in red, you can follow, there's 3 features here. And in blue, you have the wet-dry cycle, so you can see what's happening in the pond at the same time. What happens is as your pond dries up, you get to your maximum concentration of adenine, and then the pond dries, UV photodissociation is turned on, and it blasts away your adenine to an amount where your incoming adenine rate matches your photodestruction rate. Then your pond fills up again, you dilute, and then this pattern continues on an annual basis, and it never changes. It never gets any more concentrated. Now notice what it says on the y-axis there. That says adenine mass fraction, ppq. That's not a typo. That's parts per quadrillion, which is completely negligible. So what this says is that you're never going to get a concentration of nucleobases in warm little ponds from IDP sources. They simply rain down onto the surface too slowly, and the destructive forces within the pond are too efficient at removing them. But what about meteorites? Here we compare meteorites to IDPs for the pond concentration. IDP curves are on the lower half, and the meteorite curves are on the upper half. And notice the stark difference in your maximum adenine concentration between these 2 sources. So what's happening here? Well, meteorites deliver a large sum of nucleobases on the order of milligrams in one single event. Those nucleobases outflow from the pores of the meteorite and get up to parts per million level concentrations and then begin to dilute from there. And parts per million is still quite low, but it's on the lower end of what you can actually do perhaps a chemistry experiment with. But there's still some issues. Notice the red curve there sharply declines at some point. That's when photodissociation turns on, and it's completely destructive. So you need a solution. Any surface model on the early Earth needs a solution for the photodestruction problem. We like to think of sediment as being a possible solution. Sediment is everywhere in the wind. It's going to fall into ponds, and it's going to create a layer at the base, which could possibly shield nucleobases from photodestruction. It only takes about 1 millimeter to completely attenuate UV light. The second most destructive sink in the pond is seepage through pores in the base of the pond, and that's what you're seeing in that blue curve there. So we like to think of a solution for this as encapsulation, something that Dr. Christine Keating was talking about at this morning's plenary. So if you take fatty acids, which also happen to be in meteorites, in fact, fatty acids are the most abundant organic in meteorites, you put those into a pond, and all the fatty acids that are 8 carbons in length or longer are going to create spherical compartments called vesicles. And the average diameter of vesicles is larger than your average pore diameter. So this might be a potential solution for avoiding seeping through holes in the base of your pond. Okay, the last thing I'm going to talk about is actually how often did meteorites land in ponds on the early Earth, just the carbon-rich ones. We ran a probability analysis, which is based on a geophysical model of the rising continental crust. You can see in the orange line there, from 4.5 to 3.7 billion years ago, which is the interval in which we know life emerged. And we used 3 different mass delivery models, which are all based on the lunar cratering record. Now, if you're at Dr. Nicole Zellner's talk yesterday, you know that there's now evidence that there's mass delivered to the moon before 3.9 billion years ago. So we can go ahead and ignore this black curve right there, which is the single cataclysm model, and just focus on the 2 sustained declining bombardment models, the red and the blue, with the truth probably being somewhere between those 2 models. We ran the probability based on the geometric probability of landing a meteorite into a pond. And what do we find? 15 to 4,000 carbon-rich meteorites landed into warm little ponds on the early Earth from 4.5 to 3.7 billion years ago. So this is good. We know that this did happen, and the truth is probably somewhere in between, probably in the thousands regime. All right, that's all I have to talk about. I'll just summarize my results quickly. We find meteorites are a plausible and probable source for parts per million level concentrations of nucleobases in ponds. IDPs, however, the nucleobases delivered by these produce negligible concentrations within ponds. So we can forget about IDPs as being a source of nucleobases for pond environments. We get natural seasonal wet and dry cycles in ponds just from seasonal precipitation changes. The 2 main problems with this surface model are UV photodissociation and seepage. We think possible solutions for those are sediment and encapsulation. And finally, we find thousands of terminal velocity carbon-rich meteorites landed in ponds on the early Earth, giving life thousands of opportunities to fail before perhaps succeeding in one of these ponds. Okay, thank you.
We have time for one quick question while Dr. Deamer comes up.
So I was just wondering, you're showing wet-dry cycles on the order of years?
That's
and
right.
What we've been talking about, most people have shown wet-dry cycle on the order of days. And so if you did have wet-dry cycles daily, how long would it take for photodissociation to occur?
So every time you dry up your pond in our model, we turn on photodissociation, and it only takes a matter of hours for it to destroy pretty much everything in your pond. So in the case, if you had a daily wet-dry cycle and you landed a meteorite in that pond the day before, it's gone by the next day. Yeah.
All right, we have to close that up for time. Dr. Deamer, if you want to come up. Thank you, Ben.